Okay, so last time I promised you to show you other types of proofs which don't just directly prove the statement that's under the quantifier, but do some manipulation, logic manipulations to get some equivalent statement that's easier to prove that, and then conclude the original one. So probably the most common one is proof by cases. And we do this kind of proof when we have something that's an implication, but the first part of the implication has several parts. X is either something or something or something, implies something else about X, and when we are doing proof by cases, we could prove it by assuming all those parts of the OR separately and proving the result from each one of them. And if we do it for every single one in the OR, then we can conclude our answer. But this is confusing the way I am describing it, so let me go on and give you an example. So here will be our proof structure. We will, as usual, start with universal instantiation. Then we will prove our implication assuming the first part. Then we prove it assuming the second part. And then finally, we will use universal generalization. And there can be more than two things. It could be G1, G2, G3, whatever it is. Okay, now comes the example. So let's prove that if you take an integer and add to it the following integer, you will get an odd number. So what does it mean? Let's think for a moment. The theorem is saying that that phenomenon that you add 2 and 3 and you get a 5 which is odd, and you add a 3 and 4 and get a 7 that's odd, and you add 10 and 11 and you get 21 that's odd, is a general phenomena. If you take a number and add to the next number, then you will get something that's odd. So let's prove it. And now I am already not writing names of some of the steps because you've seen them before. For example, we start by suppose n is an arbitrary integer, and by now you've seen it enough time to say, oh yeah, that's when we are doing universal instantiation. And now is where universal instantiation comes in handy, because if we're talking about all numbers, we cannot say whether all numbers are even or odd. Well, some are even and some are odd. But if we are talking about a specific number, even if we just have a name for it, we could say, okay, that number may be even. If it's not even, then it must be odd. It's one or the other. And we could prove our statement for even n, and we could prove our statement for odd n, and then we can conclude that our statement holds generally. So here we didn't even write down if n is even or n is odd, then n plus 1 is odd. But every number is either even or odd, so we could introduce it. So let's now do the proof. Suppose that n is even. By definition of what it means to be even, n is equal to 2k for some k. So the next integer over is 2k plus 1. So again, we use definition, we use existential instantiation to give that name k to that number that divides n and gives 2. So now we know that our number was of the form 2k. The next number was 2k plus 1. We could take their sum and get 4k plus 1. Here we are just using axioms. We are just using algebra. Now, can we write this number of the form 2 times something plus 1? Yes, we can if we make that something to be 2k. And let's call the thing L so that so as to make our universal generalization a little easier. So the number which is x plus the next number over is 4k plus 1, which is equal to 2l plus 1, which looks exactly like an odd integer by definition of an odd integer. And now we are doing existential generalization to say, oh yeah, so n plus n plus 1 is odd. So when n was even, n plus n plus 1 is odd. Now suppose n is not even, suppose n is odd. Again, we use definition of integers, existential instantiation to get n equal to k plus 1 for some k. And the next integer over will be 2k plus 2. You sum them up, you get 2 times 2k plus 1 plus 1. And in this case, that number that witnesses that this is an odd integer, that number L, is 2k plus 1. What I mean is that we could write our number n plus the next thing over in form 2l plus 1, where L is 2k plus 1. Now we can apply the definition, existential generalization, and we again get that n plus 1 is odd. Now we exhausted all the possibilities because every number is either even or odd. And that means that it's just odd without any additional assumptions. And therefore, we can use universal generalization and say that for every integer x, x plus the next one over, x plus 1, is going to be odd. So this was an example of proof by cases. Now let's do another kind of proof, a proof by contraposition. So proof by contraposition relies on the equivalent that we actually proved again when we were doing direct proofs, that if you have g of x implies h of x, it's equivalent to not h of x implies not g of x. Why would you want something like that? A lot of time, if your g of x and h of x have universal quantifiers, it's pretty hard to reason about them. But if you take their negations, those universal quantifiers become existential. And now you could use your existential instantiation and generalization. And that becomes quite useful. So here is the structure of the proof. Again, you start with universal instantiation for all x. Then, rather than let n be arbitrary elements such that g of n is true, you say, suppose n is an arbitrary element such that not h of n is true. And from that, using again theorems, axioms, definition, you derive that not g of n is true. That gives you that not h of n implies not g of n. And now you could conclude that g of n implies h of n because that's a contrapositive, and we know that we are equivalent. By universal generalization, the formula is true. Let's do an example. So here's what we will prove. We will use definition of even that I'm not putting on again because you've probably seen it a number of times so far. Let's prove that if a square of a number is even, then the number itself must have been even. You all know that if you take an even number and square it, you get an even number. But here we are proving the opposite direction. The only way a number that's a square can be even if it's a square of something that was already even. But the way we will show it that if the number is not even, then its square is not even. And here we will rely on not even being odd, and we will prove that a square of an odd integer is odd. You see how it's much easier to talk about taking an odd integer and squaring it rather than taking a square root of a number and hoping that it is an integer. So let's do the proof. Let n be an arbitrary not even and therefore odd integer. by definition, n is equal to 2k plus 1 for some integer k. Now let's take n squared. Since n was equal to 2k plus 1, n squared is 4k squared plus 4k plus 1. That's your usual algebra. And we could write it of the form 2 times something plus 1, which, as we've seen before, means that we got an odd number. So here it is. We started assuming that n is an odd number, and we showed with just a few calculations that a square is an odd number. So a square of an odd number is odd, which means that the only way a square of a number can be even if the original number was even. And we get the statement by universal generalization. So now let's prove another thing that we already proved before, but now we'll try to spell out the steps. Remember that we had that puzzle about pens, that there are at least 2 people in our class that have the same number of pens. And we solved that puzzle using the pigeonhole principle, which said if there are n pigeons, and there are only n minus 1 places for them to sit, and all pigeons are sitting somewhere, then at least one of those pigeonholes, one of those places will have 2 pigeons. And pigeonhole principle, remember, didn't say that every nesting spot has to be occupied. It just said that there is no possible way that there would be no place with 2 pigeons unless either some pigeons are flying or there are at least as many pigeons as pigeonholes. So let's go and prove it. So I'm not going to bother writing it in the logic form, even though it's not a very long formula, but just to fit it on one slide. So here is the theorem, the pigeonhole principle. For any n, if there are n plus 1 pigeons and n holes, then if every pigeon sits in some hole, then there is a hole with at least 2 pigeons. Universal instantiation, let n be an arbitrary integer. And instead of showing that if every pigeon sits in some hole, then there is a hole with at least 2 pigeons, we will show the contrapositive. If every hole has at most 1 pigeon, then some pigeon is flying somewhere. So here is a proof, and the proof is, again, just calculations. If every hole has at most 1 pigeon, well, there are n holes, and so there would be n pigeons sitting in the holes. But we have n plus 1 pigeons, which is more than n. N plus 1 minus n is equal to 1. So there is at least 1 pigeon that's not sitting in a hole and flying somewhere, and that proves our contrapositive. So if every pigeon, so we prove that if every hole has at most 1 pigeon, and there are n plus 1 pigeons and n holes, then some pigeon is flying somewhere, which means that if no pigeon is flying, if every pigeon sits in some hole, then some hole has at least 2 pigeons. And by universal generalization, we are done.